Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tare. This is my continuing feature on the Math Lovers book, 3-volume series I wrote from 2019 to 2022 that's available on Amazon.com, both in Kindle and in paperback format. You might want to check it out. Anyway, today I'm continuing my feature on logic, chapter 7, and today I'm going to talk about logical identities, which are a very important tool in making logical arguments, as we'll see in a few lessons. Anyway, let's begin. So, what is a logical identity? A logical identity is really just another name for a tautology. Yesterday I talked about tautologies and contradictions, but logical identities are very useful tautologies. They're tautologies that are pretty easy to memorize, and they're used a lot in making logical arguments. And we'll see how that's done in a couple lessons. And today, I think it's going to be a pretty short lesson today. I'm just going to say what these logical identities are. Their names, they all have, most of them have Latin names, and also, try to explain them why they're true. And that'll be good. So anyway, here's a useful list of 16 logical identities. And like I said, they all have names, and some of them are pretty obvious. I think the first few on this list are pretty obvious. The first one just says P is equivalent to P. That's pretty obvious. I mean, every logical statement is equivalent to itself. And you can substitute anything you want for P. It doesn't even have to be an atomic statement. It could be like, I'm making this lesson right now. Well, that's equivalent to itself. Or it could be something that's false. It could be, I have a unicorn in my office. That's equivalent to itself, even though it's false. So that's a pretty obvious one. And then the next one's double negation. This is pretty obvious too. If you put two nots in a statement, like if you say it's not the case that I'm not in my office, that's the same thing as saying I'm in my office, right? Double negation. I think that's pretty obvious. And the next one, I might have gone over these next two last time, but P and P is equivalent to P. I mean, saying a statement twice. So, like, I'm in my office and I'm in my office. You haven't conveyed any extra information with the second statement. So, you're really just saying I'm in my office. That's another way of saying that this conjunction is equivalent to the just one part of it. And similarly, if you put or in there, it's also equivalent. So, I'm in my office or I'm in my office. Well, it means I'm in my office. The only way that could be false is if I'm not in my office, right? The same is true if you put and in there. And then they get a little more complicated after that. So number five. This one, number five and number six are just associativity. And these are useful characteristics of conjunction and disjunction. And you should think of these things as operators, kind of like you think of plus, minus, times, and divide as mathematical operators. You can think of, these logical operators and or and not, and the other three I gave you, equivalence, if then, and exclusive or. Just think of those as like mathematical operators, except they work on Boolean expressions instead of, numerical expressions. And I think you guys all know that addition and multiplication are both associative, and so are conjunction and disjunction. And an or are associative, just like plus and times, and it's pretty easy to check this. And these identities are nice because you don't have to just do it for three. You can do this for as many as you want. You can group a bunch of ands and a bunch of ors together. It doesn't matter how you group them. And then commutativity as well. It turns out that and or are also both commutative, L7 and L8. Just like addition and multiplication are commutative. And or are also commutative. And then we have distributive rules. And remember, we have the distributive rule of arithmetic for addition and multiplication. A times B plus C is A times B plus A times C. And it works in that order for plus and times. It doesn't work if you go the other way. But the nice thing about distributivity of and or is you can go the other way. So it's true that P and the quantity Q or R is the same as P and Q or P and R, but not only that, it's also true if you reverse the roles of or and and. So you get actually two distributive laws here. And then there's these 11 and 12 are important ones. These are known as De Morgan's laws. It turns out if you negate, if you have the negation of P and Q, that's equivalent to the negation of P or the negation of Q. This is almost like distributivity of negation. I mean, it's almost like minus 3 plus 5 is minus 3 minus 5. That's kind of the way to think about it. Not flips and an or inside the thing it acts on in parentheses. Maybe that's the easiest way to think about it. But then everything gets negated inside as well. And that's true in the converse is true as well. Not quantity P or Q is not P and not Q. So these are both very useful identities, and you'll see these a lot, actually. And they're not too hard to memorize, especially after you've used them a lot. They kind of make sense. So I think so far, all these first top 12 logical identities, they're all kind of intuitively obvious, I think. There's not that much to memorize. Just remember, the first four I think are pretty obvious, and then 5 through 8 are just like, or 5 through 10 are kind of like regular properties you learned a long time ago for numbers, associativity, commutativity, and distributivity. And then we have these De Morgan laws, which are sort of like how negation works inside parentheses. So anyway, and then what else do we have here? We have the definition of implication. This one's a little tricky. Remember, implication was a little bit of a controversial one because when P is false, you just have to kind of arbitrarily if P is false and Q is either true or false, we say the implication is true. Well, it turns out with that definition, P implies Q is the same thing as not P or Q. Either P is false or Q is true. The only thing that can't happen is that P can't be true and Q be false. That's the only case that's false, and it turns out that if you did not P or Q, you would find that's the case as well. So this one, I think, is a little trickier, but once you kind of get used to implication, I think this will make more sense. And then number 14. These in 14 and 15 are two equivalent ways of defining equivalence. So to say that P is equivalent to Q is the same thing as saying that either P and Q are both true or their negations are both true. And I think I went over that last time. I mean, that's kind of the definition of equivalence. It just means that P and Q are equivalent logical expressions. That means they're either both true or they're both false at the same times. So they're basically the same expression in disguise. Maybe that's a way to think about equivalence. And I think L14 kind of conveys that. And there's another way you can define equivalence, double implication. P is equivalent to Q is the same thing as P implies Q, and Q implies P. They both imply each other. And that's why I said sometimes people write the double arrow instead of the 3 lines for equivalence. I guess it depends on your personal preference. But anyway. And then the last one I have here is the definition of exclusive or. So this is the only one here. I think I've included every operator we've talked about so far, except exclusive or. The last one is just the definition of exclusive or. And remember, exclusive or is the opposite of equivalent. So P exclusive or Q is only true if either P or Q has to be true and not P, not quantity P and Q. So P or Q, but not both. I mean, that's basically what exclusive or means. So anyway, I don't think these are that hard to memorize. Just remember, most of them, they're either analogs of other equivalent identities in arithmetic, or they're just definitions of some of these operators. So, and we'll use these a lot. I mean, these are very useful. If ever you want to, do a logical argument, then you'll use these as tools. And it turns out these aren't the only tools we're going to use. There's also tools known as rules of inference. Those behave a little bit differently than logical identities. I'll go over those next time. So anyway, logical identities and rules of inference, those are kind of the tools we use to make logical arguments. And that completes my video for today on logical identities. Thank you for watching. Long live math, and I'll see you guys next time. Bye.